Welcome to you all to second day of 5 days capacity building event on digitizing industrial motor system for energy efficiency. This event is being organized by Shark Energy Center, and we have 8 speakers from various countries, and Mr. Hugo from Scotland China is taking the lead. Yesterday, the theme of the session was efficient motor system approach. That was covered by 2 speakers, Mr. Konrad Werner and Mr. Rob Tyven. And he shared with us the key information, and they started from the overview of motor system, and they gave us some insight on the global electricity use. And next, Mr. Konrad explained about the standardization of motor system, IEC and ISO for electrical and mechanical component. Then he explained about the minimum standard requirement for a motor, and as well as he said super premium efficiency of IE4, which was launched by IEC in 2014, and the developed countries have been adopting that. So then in the second slot, Rolf took us through the very important aspect regarding energy efficiency. Today we have 2 slots, and first slot will be covered by Mr. Hugo, and he will be talking about, he will be taking us through the digital live training using form demonstrator training facility. Then in the second slot, we have Mr. Teja Parna from ABB. He will be talking on the IoT, Internet of the Thing, in the perspective of ABB motor system. So, dear participants, now I'd like to invite Mr. Hugo to start the presentation, and in his presentation, he will be explaining, and he will be using the maybe online platform. So this software you have uploaded in our website, and you may use that later on. If you want to go with the trainer, then you can also use that. Okay, Mr. Hugo, please go ahead.
Okay. Can you see my screen now?
Yeah.
Okay, so maybe. Okay, so I can start. Okay.
Yeah.
So good afternoon, everyone. I think right now in Beijing time is quite evening. So I'm Kubo. So we met each other yesterday, but today I will start my speaking for the pump system energy efficiency and smart pump demonstrator, which is I think it's a very good example for international cooperation between China and Switzerland. But let me first introduce myself. Actually, Tula already introduced my information, also my profile to all of you, and also you can see my profile on website, trainer profile. But I can summarize my role into 3 roles. First one, I'm a researcher. I'm a researcher for the motor system energy efficiency in the factories and also to standards and labels. And second, I'm working for a lot of appliances, refrigerator, conditioner, energy efficiency standards and labels. I work with China National Institute of Standardization in this field. Third is the cooling efficiency, because the cooling products like air conditioner, heat pumps, and also the room air conditioner, everything that I think consumes a lot of energy. And finally, I also studied the industrial IoT standardization and also maybe some international standards. I think that's my research area. I'm a programmer too, and I will show you maybe on Thursday and Friday, because I did some programming with C++, or C#. I think C# is a quite good language for the industrial digitalization in future, and also I can do the programming for the embedded device and system, and maybe I can show you later. And also some IoT cloud server called OPC UA server I will introduce on Friday, and also I can do some web application and also web crawling. So I'm going to show you today, and also maybe next 2 days, everything has been coded by myself. I think coding is quite interesting and also quite important capacity for view, and also for the, of course, for the digitization world, it's quite important. Finally, I'm coordinator. I'm coordinator for the international cooperation projects between the South Asia or Southeast region, and also for ASEAN region, also maybe with Europe, and also with USA. I manage a lot of international cooperation projects, and also we did one example for technology transfer, as we transferred one technology from Switzerland to China, and I will introduce you later today. But today's session, I will see myself to be a researcher. In next few days, I will be a programmer, and I hope that my presentation can benefit your thinking. And this is the table content I'm going to introduce. Saying the first one, of course, I highlighted already yesterday, which is the motor efficiency is the key approach. That's what I always highlight, not only by me, but also by Conrad and Rolf, I think by other energy efficiency experts. I think the motor system efficiency is a key approach. Second, from my understanding, is training. I think from my point of view, training is the most cost-benefit method to improve the motor system efficiency in industries or also maybe nationwide. And I'm going to introduce a smart pump demonstrator, a good case, the international cooperation between China and Switzerland. And then I will introduce you very detailed information of our smart pump demonstration platform called Smart Pump Demonstrator. And finally, not finally, but the next step, I will show you the real case, how we can use pump demonstrator to show that, to improve our pump system efficiency case by case. Finally, I will introduce you a very innovative international cooperation pattern between China and Switzerland with national cooperation and local research and development support between China and Switzerland. I hope that we can continue such kind of innovative international cooperation in future between China and also in South Asia region countries. I think that's a table. That's a summary of what I'm going to introduce to you today. First, I think Conrad Rolf mentioned several times, that pumps, fans, and air compressors are the three most important motor systems in industries. My summarize is that fluid systems, pump, it transfer the liquid, fan, air compressor, air. They are all liquid systems. Right? I can call it fluid system. My summarize is fluid systems consume the major industrial electricity. More than 75% from pump, fan, and air compressor. I think Rolf and also Conrad show something different of the proportion, but I'm going to show the proportion of China industrial motor system and its consumption. I think it proves the same proportion, but maybe a little bit slightly. Internationally, air compressor consumes more, but in China, the pump consumes the biggest proportion. So that means in the future, we have to focus on pump, fan, and air compressor system. And also we provide you three materials. I think here in this kind of webinar, we provided three materials. We translated from Swiss Top Motors program supported by Swiss government. It's for free. It can give you something different. Okay, it's not a problem or approach for motor, but also fluid system. This is our called system approach is a key factor. I think motor plays a key role in this process because it's it's a boundary between the electrical world and the mechanical world. Actually, like Conrad mentioned yesterday, it's a split line between IEC and ISO because IEC is responsible for everything related to electricity, and ISO will take the rest. And ISO and IEC are working together for the motor system efficiency work. I think Conrad is taking the lead for this project, but our motor system, I think, could follow the same approach. I think electricity comes from grid. It goes through the transformer. It will go through VFD or not, because VFD is not the must-have, product, but it's better to have. Then it goes to motor transfer the electrical energy into mechanical energy. Then this mechanical energy will be transferred by the transmission, gear with belt, also with direct transmission, and then it will transfer to the connected drive. Could be the driven system, could be pump, fan, and air compressor. Then the fluid, the water, air, or some other liquids will go through the pipeline and also controlled by the valves. And finally, it approach to the end consumer, to remove the heat, and also the compressed air will take can execute some actions, and also it can finish every job that it can do. I think that's a whole chain, and we have to analyze whole chain to improve efficiency. That means according to the water barrier efficiency, the system efficiency is a multiplicated result of all components efficiency. The second is the lowest efficiency component beside the whole system efficiency, because barrel effect. Everyone knows that. We don't have to repeat it again. So even we have high efficient motor, but like Rolf mentioned yesterday, if our belt is way belt and also has very low efficiency, that means we will lose a lot of energy on the belt. Then we have to focus on the whole system efficiency. And also the last one I want to highlight is that replacing the high efficient motor has limited improvement of system efficiency. Like I mentioned here, and also proved yesterday by Rolf, and I'm going to prove again, and again, because we always like motor system, we put too much effort on motors, but actually motor is just one part of the system, and motor efficiency actually is quite, from my point of view, motor is a very good product. It has very high very high efficiency from the electrical energy to mechanical energy. I think that's what we have on highlight again. This is IEC motor efficiency classification, already shown by Rolf and Conrad several times. I want to highlight that here for the low power, like below 1 kilowatt or below 5 kilowatts, I think the efficiency improvement by replacing the high efficient motor, I think it's okay. But when you go to higher than 20 or even 100 kilowatt, you can see that the difference between IE3 or IE2, like 1 to 3 points. That means the manufacturers, takes everything they can to improve the efficiency of the motor by 2 to 3%. And also that's the efficiency classification difference between those, those supreme or also maybe normal motors. So that means the improvement of efficiency of the motor is quite limited. So we should not only focus on motor, but also the whole system. This is one diagram I think already exists for more than 13 years. Actually, it's from Conrad. From his point of view, if we only focus on the savings from the electrical motor, we can have very small savings, like the green circle. See? No? Okay. Then we have the core system, which is motor system. Maybe we can have the motor plus the pump from ASD. AS actually is VFD, it's a variable speed device. Then we can have some good fittings with the blue box. But if we enlarge the boundary of the system to a larger part, then we have the total motor system with transmission, with gear and box, even with some load control. Then we can have large cities. I think that's what I always want to highlight in last presentations. But my information I want to send to you is that the last sentence is below. It's considerable energy saving can be achieved by low or even no cost. That means by training, by management, not just by replace the inefficient product with high efficient product, because it will need a lot of initial high investment cost. We have to, to think about the low or no cost. The next step is how to, to achieve the goal by low or even no cost. I think from my point of view is effective training. We did a training in factories for last years in my city, and also with a lot of international trainings. The training with you is one of them. And Rolf and I visited one chemical factory and train engineers on management how to save energy in your factories. In the second graph, we train, we train the engineers how to measure the electricity with the power meter and how to analyze the data. Then we organize a webinar in industrial zone to show them how to save energy. Finally, we did the same thing again and repeat again. It proves that the training is quite effective. But the problem for us is that we have limited human resources. We are limited. We cannot train every factory by my own. Then I think train a trainer. I would like to retrain a group of good trainers. They can train the trainees within the area, within their country, within their factories to improve the efficiency. We call train the trainer approach. And then previously we train people with presentations, with slides, with everything that on the paper, called text training. And I think in 2015 or 2014, one professor here, Professor Christopher Besson from one university from Switzerland, he invented such kind of interesting, called it pump demonstrator. There, they built a small training facility with one big pump plus 4 small pumps to simulate the majority cases of the operating cases of the real pumping world. Then he installed meters, and also he installed the meters, he installed everything in the lab. Then they can train the students and also engineers for factories to show them, they can handle the valve, they can handle the frequency of the VFD, they can turn it on and turn it off, they can change the workload, then they can have very good training experience with trainees. I thought that's the next generation of training. I think a lot of people already experience those kind of things, but for the motor efficiency, I think this might be the only one machine in the world to train people with demonstrator. I think in 2016, I visited Professor Christopher Besson's lab here. I'm there. I'm operating the machine. I'm operating the pump demonstrator. I think it's really good. Then I decided to try to to transfer or bring this kind of demonstrator to China. And finally, we succeed with the support from the Swiss government and also with China local government. We have the China called pump demonstrator China version. This is the China version. We follow the similar hydromechanical design from Swiss version, one big pump plus 4 smaller pumps, but with equipment and also motors, VFDs, and also the meters, everything we can buy from China. We don't have to use the same Swiss equipment like a motor. Everything like Swiss version, we use the Chinese version. We built the similar hydromechanical stuff in China, and one big pump plus 4 small pumps. They can simulate operation loads of the industrial pump systems. I think it's operable and adjustable. That means we can change the frequency here with control panel from the VFD here, and also we can control the valve here, and also we can control the valve of each individual smaller system. I think somewhere in the middle here, it's mechanical valve. Then we can disclose information to to the trainees. And my innovation, because my problem is that we are a small city, because China is quite broad, we cannot bring every trainee to my labs because it's costly to transport people to the laboratory. It's not like Switzerland. Switzerland is more or less quite small. We cannot bring all the people to here. Then we have the Chinese version. We have the innovation of digitalization plus remote control. Right? We have the instant data sampling, and also we have cloud data received and also published service. I think we have the web portal, and also we have the professional software portal, and also from the wider range point of view, it can be can be expanded to any industrial motor systems, similar the range. And every knowledge I learned from this project, I can show you in the next 2 days. But first, I will focus on the efficiency of the motor. But the next 2 days, I think we can focus on the. Oh, okay. I got some message. I think that it's okay. Well, I will share you in next 2 days. I think that's the introduction of the pump demonstrator, the China version, and this is a 3D. Maybe this is it's a real stuff, and this is dimensional 3D. This is a big pump, and also 4 small pumps in parallel. This pump can run independently because it can run without any problem. Those 4 pumps can, in industrial applications, especially for such kind of ventilation circulation systems, we have only not 1 pump, but have multiple pumps. then we have the chance to introduce such kind of simulate industrial operation node. Then we can disclose the facts to the to the students or to the trainees. And here is small meters, and this is a general pipe for the small pumps. This is a basic design. And also our innovation is called digitalization and standardization. First, we choose smart meters and sensors. VFDs, we choose ABB VFDs because ABB VFDs we can connect with a Modbus port to sample the data. Then we have smart flow meter. Then we have smart pressure meters, and then we have the smart, the power. I'm going to introduce it to you later, maybe not today. I think Thursday, and then everything will be connected to a data gateway. We develop a data gateway by our own. Then we transfer the data via the Wi-Fi network, to the cloud server. The cloud server receives the data, then put it to the OPC modeling, and then it publishes the data to graphic and dynamic client. This is professional client, and this is web client. And this is, I think, the whole chain of digitalization. That's what I'm going to introduce you later. But today, I just bring you the framework of what I did in last years. But in the next sessions, I will introduce you some specific technologies, especially how the Modbus, being, interpolated, and also how the OPC architecture means. I think I'm going to introduce later. I'll check the time now, and already half an hour. And we built a global accessible web portal. That means from the web portal, you can monitor and also manipulate the system remotely. And I invite you all to open this link. I think we already shared the link with all of you. Maybe here. I think we already shared you with links. I invite you to open this web portal, because right now I'm going to introduce this web portal to all of you. I will click it up. We call it smart pump systems. We have to, you have to register, and also we have to log in, because already registered trainer. But for you, you can register as a new user. You can register your own account. Then you can use the system. If you're not registered, you cannot use the system. Okay.
Sorry to interrupt. Dear participant, this link have uploaded in Jans. You can see in the webinar control in Jans out.
I can copy this link to all of you to send to all the people.
Yeah.
I will send to all the people.
They can also found in the Jans out section.
Okay, I sent the link to Tula. You can transfer this link to all the participants here. Maybe I can stay here for some minutes, because you can register, and also you can access the system, because I'm going to introduce you in future. If possible, you are allowed to use the system to train other people, because we have two roles. The first one is trainer, another one is trainee. Later I will show you some difference between trainer and trainee. Trainee has the less control of the system, but trainer has good control of the system. Okay, I can stay here for 2 to 3 minutes. Maybe you can send me some questions, or we can stay here for a while. Okay, I assume that you all, already registered, or maybe later you experience such kind of this platform. Then you can log in. Okay, first you can find the introduction of the pump demonstrator in text. I think that's I explained everything in this kind of short text. And then we can start experience. Right now, we have the instant status. You can see we have the meters, instant meters. We can see the hertz means the frequency of the VFD, and also we have the VFD's power, and also we have the flow meter, and also we have the pressure from the pressure meter. Then on the ground we have the dynamic data, because right now it's not real connected, because this pump demonstrator is under migrating from one place to. I donated already this pump demonstrator from my company to my university in my city. I think we are migrating. We are migrating this pump demonstrator from one place to another. But here is the difference. For the trainers, we have the management function. The first one is gate management. We don't have the management data, and VFD operation. But actually, if the real pump demonstrator was connected to server, I can change the frequency here. Then if I send this, the frequency of the VFD can be changed remotely. That's remote control. And also I can turn it on, I can turn it off, because we have 5 VFDs. This is for the big pump, and this for small pump number 1 to number 4. Then that means we can control the VFD. Second is the PID control. It's not developed under development yet, but for PID control, I think we can maintain the flow in a specific level. That means PID control is very classic automatic technology in industries. I assume that a lot of you already understand what PID is. So I don't want to introduce PID in detail because it's a quite broad topic. But from my point of view, PID control is most useful automatic control in industries. I will introduce it later. And also we can use simulator, because right now we don't have the physical operating machine, but we can simulate the different cases, because I already record the data from previous operation. Right now we have some curves I want to redisplay. But right now I want to choose the first one. I can start simulating. Then if we go to the single pump, we can see it's changing. The data is changing. We can see that the flow goes up, the frequency goes up. Can see that the flow goes up, the power goes up, and also can change the pumps here. Because right now the data only for the big pump. For the small pump, the big pump, it does not change. We have the virtual meters. You can see the flow goes up. You can see that. And also here is instant data. This is instant data. That means we have a virtual control panel of the motor systems. I want to also show you the difference. Right now you can see that the frequency goes up. I can illustrate the frequency goes up, the flow goes up, the pressure goes up, and also the power consumption goes up dynamically. Previously, we trained the people with some slides, with something static. Right now, we can train the people with dynamic. Right now, you can see that the frequency goes up from 50 Hertz to 60 Hertz. Right now, I stopped a while, and maybe later it goes up again. Right now, I change it because we recorded that phenomenon maybe 1 year ago. Right now, I just replay it again. Then we want to illustrate you when the frequency goes up, the speed goes up, flow goes up, the power goes up, and what's the difference? I'll show you later. But I just want to let you know that this is the training facility, but this is the instant data, and also we have the data state. That means we can have the statistic data. Here we can see that in the last minutes, the phenomenon, the frequency, phenomenon of frequency changes, and also power and also flow goes up. If we refresh in 20 minutes, it means in previous 20 minutes, in previous 30 minutes. But if I change the pump to pump 1 as net, nothing, because there's no data there. If you change to big pump system. We can see that in 10 minutes, in 20 minutes. And then for this, we can zoom in to get some very detailed understanding of the data. Okay, we want to know something behind the data. And then we can show the data view. That means how the data goes up. That's the raw data of the chart. Then you can get the raw data of the chart. You can export to Excel for further analyze. I think that's an advantage of the modern technology and also the ice technology. Okay, I'll go back. It's a web platform because the pressure meter is so strange because the accuracy of the pressure meter is not as precise as possible, because if we want a very high accuracy pressure meter, the cost is really high. We cannot afford such kind of high cost pressure meter. Then we decide to to use a cheap and also acceptable pressure meter to get the data. Then we can also turn it on, turn it off. See, here is the legend of the line. If you don't want the frequency, just click, then the frequency will disappear. And also, if you don't want to see the power, and if you see the power, okay. I think this is a very good training facility. I hope that you can maybe experience a little bit, and then you will find message. Okay, more message on that side. Then you can train the people with the trading facility. But for the normal user, you cannot control you don't have option here. That's a management function, and you have to contact me to authorize you as a trainer. Then you can use this system as a trainer. The most important thing is to change the simulating curve of the system, because for one curve it's about 10 to 15 minutes. Then you can change. Right now we have about 9 to 10 cases. Then you can use such kind of 9 to 10 cases to train people to better understanding what real pump is. Okay, and this is a training facility. I will leave it alone for some minutes. Then we can find the very good curves of system operation. And then we can explain in detail. And actually, I took this classic how this first the pump goes, the frequency goes up, everything goes up. Then I keep the frequency. Then I use a valve to control the flow. You can see the the phenomenon, how if we change the valve, how the flow, how the power changes. And then if I change the frequency again back to 15 hertz, how the flows and also how the power goes down. Then we can really experience why VFT can save energy by changing the speed. Okay, this is the web portal, and this is for the virtual control panel. Everyone, I think right now we have about 50 trainees. Then you can have 50 people can see the screen, because we cannot use cannot use webcam to for each meter to web live web video to all of you, but we use this kind of virtual control panel. You can experience the real operating of the system. Let me show you. This is instant data. This instant data. You can see it's like a virtual power, virtual guard. Okay, interesting. Then we have the real capacity of remote trading. Let me show you geographically. This machine locates in Zhenjiang, a small city near Shanghai, in the east of China. And then I'm the trainer. I'm located in Zhenjiang, but my cloud server locates in Beijing, maybe somewhere else in the world, maybe Hong Kong or maybe Shanghai again. But I provide you a web portal. Everyone all over the world can access it. Here in Pakistan, you can have the trainees from India, from Nepal, from Bangladesh. And also maybe also in future, if you are the trainer, we can have a trainer in Pakistan or India to use the training facility in China, train the people in South Asia region. Of course, in future you can build their own training facility in Pakistan physically or in India physically. Then you can train the people in the region, in the local regional level. I think that's what the concept of trainer. So today I'm not training people, how pump demonstration is, but also the concept how we can train the trainees in future. You will be the trainer in future. I hope that you will be the trainer in future, not only trainees, because we cannot train the people by our own, one by one, okay? Because we're limited capacity. And then we have after training of the training facility, right now we have go to the efficient pump system. I think from this, because this is the 5 points I take from the training material of the pump system efficiency. We summarized the 5 most important points for a very efficient pump system. The first is design. A lot of people, the designer, the pump system designer always oversizing of their product. But the most important thing, we have designed the system in proper application conditions, because we have to decide the water requirement and also heat requirement for the system. Maybe at the very beginning we cannot get the requirement precisely, but after the facility was put into use for years or maybe for some months, then we can figure out the real demand for the system. Maybe we can consider about redesign. Redesign is most important to improve the system efficiency and system energy conservation. Okay. Second is we focus on loss. We have to invest on minimum energy losses layout, because we have we want here we don't touch anything about pump or the motor, because we are touching about lines, the pipe network, cross section design, to cut the numbers of throttles, because we control the valve and also even the band of network. We have to reduce the loss as much as possible in the network. We don't mention about the system again. And also the third one is variable operation, because in a lot of cases, because of temperature changes with seasons, with daytime and nighttime, and also maybe with different, the production demand. That means the demand from the pump system also changes. That means the pump system has to be operated in variable operation conditions. That means we have to adjust amount of water and pressure on the on-demand control. That means, of course, maybe the best solution or the most popular solution currently is VFD. I think the ABB colleagues will introduce this later today or on Friday. Finally, we have the frequency converter control. We have control speed of the driving motor. We don't have to use throttle or step switching to control the output. Okay. Then we have finally, the 5th step is we have to replace the inefficient motor with efficient motor, because we can use high efficient motor, adapt to the pump for the lead and speed. Later I will explain you. If we only maybe right now have one question for you to consider. Can we achieve energy conservation goal by replacing inefficient motor in pump systems with a high efficient motor? You can think about yes or no. Later, maybe I will disclose this to you. Okay. So right now we have the practice. Right now I prepared 8 to 9 practice for today's training. This is the first practice, because I want to ask questions for each practice. The question for practice 1 is how the rotating speed affects system flow, pressure, and power. The first is we have to go to this kind of, this is nameplate from one motor. I took the image from the Google search, and then we can have this kind of rotating speed information. It's 1430 or 1720. So how the ideal or theoretical rotating speed of the motor can be calculated? The RPM is rotating per minute. The formula is calculate this is the 60 multiplied the frequency. Normally 50 or 60 in China, 50 I think in US or Japan could be 50, and also multiplied by 2. Then it's divided by the poles. Normally we have 2 poles, 4 poles, 6 poles, 8 poles motors. Then we can have the ideal or theoretical rotating speed of different poles under 50 Hertz frequency. That means 2 poles is 3,000 rotating per minute. The 4 poles is most popular. It has 1,500 rotating speed per minute. And for 6 days could be calculated correspondingly. And why this is in theoretical, it's 1,050, and here is only 1,430 because all the induction motor, because the induction motor is most popular technology of induction motor. It's called asynchronous motor. That means it cannot reach the ideal or theoretical speed because it always, the rotor always catch up with, the speed of the magnetic field. Then it's always some difference between 150 to let's 70% rotating per minute is difference. And then the higher efficient motor has less such kind of difference. That means the high efficient motor has, for the same size, same frequency, has higher rotating speed. I think this point can tell you why we cannot achieve the system savings by replacing the motors. And I think Rolf yesterday already introduced how to calculate the efficiency. Here is for the lamp plate, it's high too. That means it indicated the efficiency, but also with currency, with the output power, with the continuously power factor, and also the voltage, you can calculate the motor efficiency. Okay, I think Rolf introduced this yesterday. I don't want to repeat this again. So that's the second slide of the same question. Normally, for the pump system, we have 3 most important parameters. The first one is flow. The second one is pressure. Finally, it's power. Actually, when the frequency of the induction motor actually decides the output also of the pump systems. Here, oh, maybe here it's wrong. Here is 1. Okay, here is 1. I'm the mistake. The flow goes up or changes with the speed. Actually, the frequency means the speed. If the speed goes up, V1, then maybe not. Okay, suppose V1, V2. Okay, if the speed goes up, then the flow goes up in linear proportion. But the pressure goes up with the speed changes with square, and also the power actually is decided by the cubic changes. I think that's called affinity law. You can search this on internet or Google it. Then with this, you can see that the blue dot means, and the x-axis is frequency. Y, the blue dot is I think that blue dot. I think the green dot is the flow, goes up. Then the pressure, even the accuracy is not very good, but still goes up, and also power goes up. Okay, and this explains this phenomenon. And the second question is replace the inefficient motor with efficient motor can save expected energy. But for the pump system, I think my answer is no. Here is one example from the pump demonstration show. Here is the operating status when the frequency is 20. That means at the frequency of 20, the power is about 130 watts. The flow is about 30 to 30.3 cubic meters per hour. And if we replace the inefficient motor with high efficient motor, normally the high efficient motor has 3% higher speed. That means the frequency of the system will goes up by 0.6 hertz. Then the flow goes up by 0.3 cubic meter per hour, and then the actually output power increases to 141. That means right now we have 12 more power consumption of the system if we only replace the motor with high efficient motor for the pump system, only for the pump system, also for the fan, but not for the air compressor or other mechanical motor system. But for the pump, for the fluid system, if we replace inefficient motor with high efficient motor, which will cause the rotating speed goes up, means the total output power goes up. I think Rolf highlighted already yesterday, but today I will use this, this pump demonstrator to disclose in more detail with case for all of you. Okay, and this is a fact. It's from the material. That means the increased number of revolutions with normally for motors could be 1 to 5%. The increased input and output power of the pump actually is not linear. It's it's cubic proportion. And if we increase the rotating speed by 1%, the output power will increase by 3%. If we increase this by 3%, then the power increase by 9%. Actually, I invite you to make a general calculation. Here we increase the rotating speed by 3%, means 3%, 20 multiplied 0.3, that means 0.6 hertz. Then the power goes up from 130 to 141. If you divide, use a cell phone or other tools, you divide to then the answer is 9%. Or around, that's real exact 9%, but around 9%. I think I use the case to highlight this fact, and also I want you to avoid make such kind of mistakes in your retrofit of the motor systems, and also maybe even in the policy making process. I know that some of you come from the government agencies, okay? And then is how the valve control affect flow, pressure, and power. And we have different sections here. When the frequency, the blue line is the frequency. It goes up. The flow means yellow dot goes up, and also the green goes up. And when it reaches 30 hertz, because it's because this is a laboratory, I don't want to reach this limit, which is 50 hertz. I think 30 is good enough for demonstration. And then I stop to change the frequency. Then I start throttling this. Throttling, I use a valve. The opening rate, this is from 100% to 90% to 80%. Then it goes down, goes down, goes down, goes down. Finally, I almost close the flow, throttling all by zero flow. This flow is zero actually. This is a line 0 here. Still, I can say that the system consumes, I think, 75% of the power. 75% power. Even I throttle the system from the full flow to no flow, if we're throttling the valve to control the flow, there are still 75% of the energy still consumed by the valves, by the flow system. That means we waste a lot of energy. Then I started to, to open this valve up. Then we can see that power goes up a little bit. And then I try to use VFD to control the speed. Then I use VFD, goes down again. Then we can find that the flow goes down, and then the power goes down. Here, the power is about, let me see, it's only about 90 or 80 watts. And when it goes up, I think the difference between those lines is a saving potential between the throttling and also the VFD. Use VFD to control the speed. Okay? And then we can see that when the flow goes to the same level, 0, or maybe even higher, we can save still a lot of energy. That's why VFD can save energy. This is already as explained why VFD can save energy. Theoretical figure. Rolf, showed this figure yesterday with some theoretical analysis. He explained this in detail. I don't want to repeat again. But this is the real world. With the pump demonstrator can show the people, okay, how the energy can be saved. This is the line of the VFD. This is the line of the throttling, and the difference here is savings. We have the similar curve, but not the same, because theoretical and also the practical has difference. Okay, and this is new version. It's a new version actually. Okay, right now I think our system here, I think, operated in quite well situation. I think we can repeat this curve again. Okay, right now we have the pressure. We can see that when we use VFD to control the system, and we can see that the pressure goes up to, and then the pressure staying the same, and then when we sort up, it goes down. It's almost the same. I just make a screenshot of this phenomenon, and in future, and here you can have some data to show you. At this point, you have frequency of 30, power consumption 233, and here you have the frequency of 50, and also the power down to 75%. The frequency only 2 times, but the power goes down 4 times. It's not theoretical, it's practical. It's from the recording of the system operation. We just replay them again. I think in future you can replay this by ohm. You can do it by ohm. You can control it. And this is the main. This is from the main chart. This is power chart. We don't have power chart to this. And also the frequency base. That means XL is frequency, and the Y XL is flow, power, and also the pressure. The same. We just screenshot from our presentation. But with replay of the data we use, I think we can reach the same goal, but with some data. And this flow base, the same thing. Okay, maybe the data here is not good enough because we need long time to operate the system. Okay, I think we demonstrated the practice 4, and also this is a practice 5. How VFD can automatic control system. That's a PID control. Because I didn't include this for the phenomenon, but I can explain you that I set the system like 25. Then the VFD will change its frequency, try to maintain the flow around 25. It goes up, it goes down, goes up, goes down. Then I change the setting to 32. Then it goes up, step by step, by 0.3 Hertz. And then when it reaches the target flow, which is 32, then it will, to keep this like like a very regular curve. You can see that the PID control can always try to maintain your system into a stable world, because the control interval of this is about 1 or 2 seconds. That's why there is always 1 plus minus 1 difference between different plus and minus 1 difference. But if we want to control, we have to change the parameter if we want to control the flow in like 8 to 10 seconds to change the frequency. We can see that the curve will be almost flat. I didn't record the data this time, but I'll just tell you that if we change the parameter of the PID control, then you can have a very good control, stable of the system in stable way. I think this is the process. I think the last one is because right now we only illustrated for 1 pump, but actually we can use multi pump. In a lot of cases, we have 1 constant pump, we have 1 fixed pump to provide the base load, but we have a variable pump provide the variable speed control to meet the variable demands of the system. And right now we have 2 pumps. The first one is small pumps 0, 1, and 3 pumps 3, and also we have small pump systems. The upper flow is flow. Flow means the I think this green blue line provide the basic load. I think this is small pump 3, and then we use the small pump 1 as a variable, which is red, provide the variable load. Then we can see, then they can add them together. The small pump systems, they can, the small pump 1 plus small pump 3 combined together for small pump systems. It will be like this one. That means where our system adapt, we have some base load, and also we have some variable load. That's a good combination of the system. Also, we can demonstrate this with numbers with pump 3 and pump 1. Okay. This is the flow. I think the power will follow the same phenomenon. And here is the base load with about 150, and then we have the changed. We have the changed load. I think about 50 watt. Then in combination we have almost 200. Difference between because the metering, the accuracy of different meters. Because system, and also we measure the flows and also power individually, then we put them together and we can calculate this out. Then I think that's how the fixed speed and bar speed can combine together, provide complexible load for the pump system control. Okay. Actually, the practice 7 is question, and also will the partial load reduce efficiency? Actually, I observed that from my analysis, we have I have 1 big power, and also we change the frequency from 50, 20, 25 to 30 hertz. Then we can have the VFD input power. Then actually we can calculate the load of VFD. It's very, very small because the frequency of 15 is really, really low, but it's not practical. It's just an experiment. Then we have the VFD output power, and also we can calculate the loss. Then we can calculate, roughly the VFD efficiency. Actually, the VFD efficiency at low loading factor, at very low load, is really low, only 40%. Actually, if the load can reach to 75 to 80 or even 7,500%, the VFD has the efficiency of 95. But when you decrease the efficiency, when you decrease the frequency of the VFD, actually the motor and the VFD, their efficiency decrease. But you got the saving from the energy because you cut the load. You cut the load from the demanding side, which sounds a little bit paradox, but it's true. Like Rolf mentioned yesterday, when your loading factor is high, the equipment efficiency is high. But when you are outputting a lot of flow, a lot of pressure, unnecessary, that means you are wasting a lot of useful fluid energy. So the first question or the first step is to resize the demands of the flow and the pressure. Then you can achieve the saving. But from the equipment efficiency point of view, it might decrease. It's something of a paradox, but I want to let you know it is a fact. Okay, the practice 8, but actually this I'm not going to go to in-depth of how the IoT technology can support efficiency improvement, but I will introduce you in the later 2 sessions. This is a practice, but our digital demonstrator already showed the advantage the IoT technology in training, because we have to learn the device communication protocol, analog, Modbus, I2C, a lot of communication protocols, and also we have to to go further step for the cloud communication protocol, which is OPCUA or other like MQTT, a lot of communication protocols. The first one is the system status or condition monitoring. I think Conrad Rolf mentioned this, and also like ABB colleagues will introduce later of their solution for status monitoring. And second is for the remote control. Actually, if the system is on operation, I can turn it on and off. I can change the frequency. I can set the PID target control point remotely. I think then we can use the data to the persistent and storage. We can save the data in files and also maybe in database. Then we can regain the data for analyze and also to get better understanding of system operation and also take actions to optimize data. I think that's evidence we have to show to to the higher management and also to the external experts. And also we can use data further analyze. Then we can develop the optimization plan. And but I think maybe in future, maybe I don't know how long it will be. It could be any efficiency AI or expert systems. We input the system, the basic data, including the model, the power, and also efficiency, and also the load. And also we can input them with power, voltage, current, power factor. Then and also maybe the flow output, and also maybe the temperature of your factory in different seasons, different daytime, nighttime. Then the system will automatically give you one solution how to improve system by operation, by resizing, redesign something. I think that's an ideal situation, but I'm afraid that it's not available on table today. Okay, and I will go back to the Swiss demonstrator again. This is the story. Maybe here, I can call it a very good international cooperation pattern, because the Swiss University, the HEIT, Swiss Western Science and Technology University, the professor designed original, the pump demonstrator. They have the original design, intellectual property, and then they authorize the IP to the impact energy. like Roth, which from Roth company, and then they have switch promoter coordinator. Then it authorized this IP to us, the China company, actually my company, which is called Signing to Zhenjiang Technology Transferee. And also we get the support from two parts. First is for the Swiss government, because we transfer the Swiss knowledge, Swiss design, then we can also translate the Swiss knowledge into Chinese, into English, then we formulate this topmost 3D material. I think Tula and also the organizer already shared the links and also shared the material on the website and also in our webinar. I invite you to download these materials and read carefully, because it's from not something that's core part from the Space Mode 3D material. Actually, we also got the research and development fund from a local government called the Zhenjiang Bureau of Science and Technology. They invested us to buy the motor, buy the VFD, buy the meter, everything, and also to hire the engineers to redesign, and also finally we build the China version. Then that's what I can show you today. I think that's a very good cooperation, international, local, from knowledge and also from the IP, and also maybe also from the research and development fund. Actually, based on such kind of development, we built an innovative pump demonstrator which available for international trading like you. Of course, like I mentioned to Tula, the organizer of this event, so we are open to transfer the hydromechanical design to the partners in South Asian region. So if possible, you can contact me or contact us via the SARC Energy Center. I think we can discuss the further cooperation in the future. We can transfer the hydromechanical design from Swiss and also the China version to all of you. You can build the pump demonstrator at least in your country, and also can share the 3D materials from us. Okay, I think I'm quite open for the cooperation, and this is my contact information. You can always reach me by the email address. And maybe finally, I think we can go back to the pump demonstrator. Let's see what happened. Then you can see it draws the same curve like the presentation we make, but we want to present in dynamic way. I think that's our approach. Of course, the pump demonstrator we have to, to experiment it for a long time. Especially we have 9 curves. Actually, I didn't show you the parallel pump separation curve. That means mount pump separation, because the time limit, because we have the time limit today. But yeah, I think we have enough time for the further communication in the future. Okay, I think that's mine. That's all introduction from my side. So I'm ready for the questions. Okay.
Okay, thank you, Mr. O, for this excellent presentation. Dear participant, you can send us your queries in chat box, or you have any question, queries, ideas, or any problem in work setting in your organization or company, then you can call in on video online.
Okay.
And you can talk to the instructor. So now,
okay.
Any question? I have sent you in your chat box.
Okay, I think here I can see that the first question is, what is the maximum efficiency of AFT itself? I think Conrad and his team is working on VFD International Energy Efficiency Classification. I think at least for the, depends on the size. The bigger of the size, higher efficiency of the VFD itself. I think 95, 96, even 98% can be reached. I think we can leave this question also to Theo from ABB, because he knows this much better than me. Okay. The maximum rating output power back to load back. I think it can be even 1,000 kilowatts. The smallest could be like 500, 300, 500 for smaller circulating pump, and also from very small pump to higher range could be 1,000, even 2,000. But I think that if we think about in the motor point of view, the small and medium size definition could be in China is point 10 watts to about 375 watts. That's the most common range. But for the motors higher than maybe 500 kilowatts, I think that's can be called some special or some particular equipment. You have to go to ABB or like Siemens to ask for their special service for such kind of big VFDs. But I believe the range could be as 2 to 3,000. It's no problem because I visited the ABB China factory. I can see that they can build the VFD more than 3,000 kilowatt. Big machine.
Okay.
Okay.
Thank you, Mr. Wu. Now I think there are no more questions with us. Dear participant, for evaluation purpose, we have few questions. So that our idea is conduct in a multiple choice question. So you may respond that question. Please. I would like to request Mr. Wahab, please go ahead.
Dear participants, thank to be with us. From yesterday training session, we have designed a small MCQ poll for you that will appear on your screen one by one. Select the option that you think is correct. Now I'm going to share the question number 1. Okay, thanks. Here I'm now going to launch the question number 2 for you.
I don't have.
Now the question number 3.
I'm not able to see it.
Dear participants, thank you for your cooperation and taking a part in this session. We will, in the tomorrow session, we will show the correct answer to you of this, and we have 3 more questions for you after this.
Wahab, what is the question?
Question number 5. And the last question, question number 6, is now on your screen.
I mute the. Wow. I mute the. Nothing. Okay. Thank you, participant, for involving in this question MCQ session. So we'll have break of 5 minutes, then again start at around 3:40. That next slot will be covered by Tejo Corner, is a product manager ABB motion service from Finland. So okay, thank you for now.
Hello, can you hear me?
Speaking.
Hello, can you hear me? Teijo Kärnä from ABB joining.
Yeah. Welcome, Mr. Tejo. Yeah, we are hearing you.
Thank you.
After 5 minutes, we will start. No, after 5 minutes, we will start.
Okay, very good. Thank you.
This is a short refreshment break.
Hello?
Mr. Tejo, are you speaking?
Yeah, I'm here. I can hear you, but I'm afraid that we cannot listen to you.
Yeah. We will start. Okay, now we are given a short break of 5 minutes, so it's almost over. So in I think we will start.
So are you asking Teijo Kärnä here? Is it my turn now?
Yeah, we can hear you, Teo.
Very
No
good,
problem.
very good.
But I
I have
think
I have just not figured out in this GoToWebinar how I present my screen.
So I think Tula, you have to give give the presenter to Teo, because currently he cannot share the screen. You have to authorize him to give him access to share the screen. Okay. Tula, right now you are the presenter, you are the organizer. You have to delegate your permission to him.
Mr. Corner, Mr. Tejo. Hello,
I think Teo right now can share the screen. No problem.
Mr. Tejo Corner.
Yes, I'm here.
Okay.
Yeah. We can see the screen now. We can see the screen now.
Very good, very good.
Mr. Corner.
Yeah,
Hello. Now audience are off, so we'll start in 1 minute. Okay, so I'll give you your introduction, then we'll start after 1 minute. Okay.
very good, very good.
So now, okay, remain here. So start again. Dear participant, welcome back. This is just for information. Our presentation slide and this video will be uploaded on our SEC website www.sarkenergy.org. As well as this will be shared to YouTube link, so you can have a look on that. Now I'd like to invite our next presenter of the day, Mr. Tejo Kärnä. Mr. Kärnä is a product manager at ABB Motion Service Division, Finland. He has completed BSc in Mechanical Engineering. He has 25 years of experience in ABB. His areas of expertise include electric motor and frequency converter in different scales, project and service management roles. He also has long experience in wind power and other renewable energy segment. Please go ahead with the presentation. Hello, Mr. Kärnä.
I'm here. Yes.
Yeah.
Can you see my screen now?
Yeah. Please go ahead.
But I cannot see my own screen at the moment, so I'm sorry, Mr. Chairman. I'm just seeing your screen. I cannot see my own screen.
You may have open. You can check over there. You had
Sir, we are saying your screen. It's a conditional motor for monitoring for motor powertrain, and there is a pop-up on your screen. So we are watching your screen. Just click on the presentation, so we will see and continue. We can hear you.
Yes, I can hear you all, but I can just see Mr. Chairman's video. I cannot see my own screen and presentation to continue.
So we have sent you the request for share your screen. Just click on the software control panel. Go to webinar software control panel. On the bottom, that it will show the screen to you. We are watching your screen perfectly fine. Can you move your cursor to the taskbar?
Yes,
Yes. Now open the GoToWebinar. Click on the GoToWebinar software.
sorry, very bad line here.
Yes, we are watching that.
So what should I press now?
You should press the GoToWebinar software.
This one, no.
You have
Sorry. Ah,
Yes. And we are now watching your screen. Just click on your presentation and continue to your presentation.
so can you see my presentation now?
Yes, we can see your presentation now. You may continue now.
Okay, good. Sorry. What is this now? This is very strange.
It's showing on your screen, sir.
Right. So you see my full presentation now, I assume.
Yes, sir.
Very good. Thank you. So sorry for this inconvenience. I would start presenting myself. My name is Teijo Kärnä. I'm the product manager for digital solutions for our motors and drives in ABB. And I would like to give you a short presentation about our digital solutions and also how we see that our digital solutions will support customers when it comes to customers to do energy efficiency upgrades. So today we have I don't know what is happening now at the moment because the screens are changing constantly here. Okay.
The screen that taking reliability. Did you?
Yeah, it's working now. Okay, please. You go ahead. The
Thank
title,
you.
yeah, title is taking reliability, isn't it? So we
Yes.
start over. Yeah.
Okay, thank you. So when discussing with customers nowadays and when it comes to digitalization, we are facing very often the same statements and the challenges of the maintenance and when it comes to digitalizations today, and especially today when we talk about the Industry 4.0. So what we hear from the customers today, we are talking about pretty much 4 different topics that constantly come up from our customer side. We talk about reliability and very often what the customer says that we want to minimize the unexpected shutdowns and maintain reliability. And this is a very typical statement and it's nothing new as such. We hear that they want to understand and solve the problems earlier and faster. This is a very typical question. And then coming up more and more today when talking to the customers that we need to optimize our limited resources. And that is coming from the demand of that the customers today doesn't have expertise anymore on site in their factories or wherever they operate. So they need more help also because they don't have the skills and as they used to have in the past. And at the same time, also we face the question about the new normal. And in the new normal, what we face today is not only related to the COVID-19 pandemic that we are seeing today, working from distance, but also with the much higher demand for health and safety on sites and for the people operating on the field. So what the customer actually want to know is to understand the actual conditions of their assets and also what is their risk exposure today for the unplanned downtime. They want to know about historic data and benchmarks to optimize their conditions, of course. They want to receive alerts and predictive analytics to maintain their performance. And they also would like to get expert advice very easily, or let's say at a click. This is a change that has happened recently because the new technology has starting to enable that kind of things. As I said, customer is facing limited resources. The motors and the drives are usually remote and in restricted locations, and they would like to focus on the actual requirements and not do time-based maintenance. And of course, they would like to avoid the global technical skill shortages, as I mentioned. Coming to the new normal, I talk about health and safety that starts to be more and more important for the customers. And then, of course, to secure the business continuity in these kind of adverse environments. So this is the typical questions and the demands and needs we see from the customers that we then try to also solve with our digital solutions. But then, what is the value of the digitalization? Digitalization is a word that is used today in many different contexts. And what we have learned also during our journey in digitalization is that this is something that is so new still that people have really not thought through the whole process. Meaning, what does it require from different stakeholders when you do the digitalization? And what is the value that it will bring you? What we have learned is that just a sensor on an asset as such doesn't actually bring so much value. A sensor that is not used is only a cost. Then when we go to the next phase of the curve, we are talking about what is the value of the data. Is there a value in the data if it's used in a very limited way? And here we come up in the discussion with the customer, of course, first of all, when discussing where should we store the data? And then, of course, what are we doing with the data, for example, if it's only stored on a local computer or a local server? What is the accessibility of the data? Who will use the data? And can the data be further developed for bringing value to the customer or the user? So what I claim to say that when the data is transformed to some kind of information, it's increase the value of the data, but it's not actually bringing the big value yet. So it's only when the information becomes an action when the maximal value is received. And how do you get the information to be an action? For there, we need to have tools, but we also need to have processes and, again, I would say, a development also among the users of the data and the information. So my statement is that to optimize the value of the digitalization, the whole organization, the process, the work methods, and the behavior of the people needs to be adjusted accordingly. So digitalization per se alone will not bring the value that it should. So a short introduction now from my side of how we see the condition monitoring for motors and drives. So we can imagine a customer case here, and this is a live case. So why to monitor the condition of the asset? And this is a real case from United Kingdom. We have a motor at a pumping station. As you see, motors, pumps, and control and VSD drives here. So if there would be no sensor, and as the customer used to have, we can imagine the situation they had. Nobody goes near the assets. This is a pumping station on a remote location. And when something failed, then the user is surprised. He starts to look for a spare part or a spare motor in his warehouse. Then he starts to look, where do I find an electrician, and beg them to come soon as possible. He needs to arrange lifting gear in place in a hurry. So it will take days, at least a day, even more, if even you have a motor on the stock. And this, of course, time and cost can easily spiral out of control. Then the customer started really to monitor the motor and the drive, and the situation changes, I would say, dramatically in the way that nobody has been looking at the motor there, but the customer will get a warning before anything happened. He could order a new asset spare part if he didn't have in the spare part stock. He could plan the intervention in time. He had reserved the engineer to come to do the job, and he can run down and run up in an orderly fashion without interrupting his production or the water supply for the community. So very simple, but a huge impact. So then extending the whole discussion to what we call the powertrain. And the powertrain in our view then can consist of these elements. A powertrain as such does not need to be a motor and a drive and a pump. It can be different kind of assets. For example, if it's a motor and a pump, then we call it a drivetrain or a powertrain, sorry. And in today's offering, we have the sensors as such. If we start from, let's say, the pump side, we will have a general machinery sensor that can be monitoring different kind of rotating equipment. We have the bearing sensor for the bearing housing to analyze the bearings between the driven object and the motor. We have the sensor for the motor itself, and then we of course have the drive, the frequency converter, where we have the monitoring and the gateway for that data acquisition. And how does it work actually? And we have to remember when talking about digitalization, there are the rules of thumb to make this happen. It has to be easy, it has to be economical, and it has to be also scalable. And the solution in our mind for that is that you need to have a system that is self-maintained. Self-maintained in this respect, how we see it, is a little bit like your mobile phone. You don't need to have an expert coming home to you when you are taking a new mobile phone in use for your personal things. So you have to be able to do it yourself, and you have to be able to do it in a very quickly. Otherwise, you will lose patience and you will lose money, and it has to be scalable for many assets at the same time. So what this means for us that we have the customer environment here where you have the different kind of assets. I'm just mentioning the drive, the motor, and the bearing, and you connect these with a sensor and data acquisition equipment. That first of all has to be, as I said, easy and economical. So you have to be able to do it yourself without bringing experts on site. Then these sensors or data acquisition equipment will then send the data to the storage. And in our case, we are talking about a cloud solution, and that is bringing the capability of self-maintainability. You have to be able to define yourself who is having access to the data, who can see the data, who can change the data, and who is the one that needs the data, and the information coming out of the data. So our solution in the cloud, we have the algorithms that are looking into the data that is coming up from the assets. We are running the algorithms, and we are then creating and visualizing the data with reports, alerts, and so on already in the user interface for the customer that see the data himself directly. Okay, in case of that the customer see that there may be issues and so on, then he can also contact ABB expert support for this kind of very tricky questions, and the expert is going back to the customer, showing and giving his response in the portal, but also the possibility to, of course, do it the traditional way by contacting a customer over mail or phone or so on. In case of that the customer doesn't take care of the service himself, he has a third party doing the service and maintenance, we can of course include this player in the game, and all this data and instructions service as such is going through a cloud-to-cloud interface through a REST API. This is in a nutshell how the architecture is built up. An example, often when we are talking with the customers about how often do you take data, what kind of data do you use, we would like to get the data every second and so on. And with that, of course, data is a cost in the end, and we start to discuss with the customer that what should we do with the data. A good example here about an electrical motor with the vibration alarm. The sensor is measuring data once an hour, and usually when a motor is starting to have issues, you can see it very early on. In this case, you start to see the changes happening over 1 month before you are even entering into the alert stage. And when you see the motor entering into the alert stage, you can pretty much also start to predict that when should I start to do some actions on site. So my point with this slide is just to show that you don't need to have the data on second, millisecond, even minutes. On hourly rate is good enough when we talk about electrical motors and predicting future behavior. So what value does this then service deliver? And I have usually categorized the values in 3 different areas. We talk about convenience, we talk about optimized maintenance, and also, of course, peace of mind of the customer. So we are then on the convenience level, we are providing the full access for the customer to see the status of his assets over the mobile or in the web portal. And we are able to deliver then reports and recommendations for the user. This will of course then bring proactive and predictive maintenance based on the historian and the trends like I showed earlier there. And of course, we can also start to look at the analysis of the outliers and the anomalies that will of course predict the status of the assets over a longer period. But in the end, the most important thing is that by this you get a faster response and protection by having an asset that is talking to you. It's bringing you errors and limits, thresholds, parameter change you can do remotely, and you get automatic email notifications if something is wrong. And of course, you have access to the experts also, and you can look at the same data together with the expert and get the recommendations. So in a nutshell then, the values, going back to the first question, that only when the information becomes actions, then it starts to bring value of the data. Today I will also state that with the digitalization, we are not doing anything such new that was not possible to do before. It's just so that we are now able to do it in a more economical way, and we are also able to, because of the self-maintenance and let's say cheaper technology, we are now able to scale it so that it makes sense to do monitoring of assets that it was not possible to do before because it was just too expensive. So it's all about managing and minimizing risks. That of course will then eliminate also inefficiencies. We are talking about the topic of today, saving energy, labor cost and so on. We are able to optimize the investments so that we really have the right size of motor and drive or pump in the operation, and then we can also of course optimize the investments. Very important thing today is that the user experience, younger people need challenges. They are not so interested anymore in just going around and doing measurements. They want to have more satisfying things to do, and the digitalization is of course providing that kind of opportunity. And of course, a very important part is that whether we want it or not, the digitalization will happen. And to be part of that race, we need to either defend ourselves or we will disrupt the market by having this kind of offering. Let's say digitalization in the future for even motors and drives is the ticket to play, because you need to have it. So here are just a few examples from our customers that they have stated. I mean, some customers have been able to reduce the downtime as much as 90% with very simple monitoring. Asset lifetime has been increased up to 30% by understanding how you are really operating your devices and doing small changes in the processes. Increase the energy efficiency, and that is happening. I will come to that later on in my presentation. So we see here customers saying they have reduced unexpected downtimes, either by 2 events or even a hourly basis, and I have reduced the inspections by 66%, meaning that he doesn't need to have so many people on the field anymore. So now I jump shortly into energy efficiency and digitalization, and what does it actually mean when you now have the possibility to understand what is happening there by sensors. So now I would claim that you use long-term data to uncover hidden opportunities, and this is the difference between the new possibilities and the old traditional way to do it. So we all know this, what this comes from. I mean, the world is evolving, and we have energy efficiency classes that was mentioned in the previous presentations. We have the Paris Agreement, UN Sustainable Development Goals, and so on, and converting combustion engines to electrical and so on. This is all visible, but then there are a lot of invisible things, hidden things, like how much energy waste do we have on the old installations? Is there new regulations coming up? Yes, the answer is that there is, but what will they look like? And security concerns about sharing data and so on. These are all hidden things still for the major part of people. So we need to change our horizon and also uncover the hidden things. This is the facts. We know that the energy demand is rising globally, and you see the trend all over. A little bit more in some countries, a little bit less in some countries or regions, but the trend is the same. There is a growth both in primary energy demand, but also especially in the electricity demand. And the question may raise that if we have the targets to reduce the CO2 emissions and fulfill the agreements that are coming from Paris Agreement or UN, it becomes also very obvious that it cannot be short-term or even longer-term solved by just renewable energy sources. We need to do energy efficiency task just to even make sure that the energy demand is met. I think that this has been a little bit discussed in the earlier presentation. I just want to bring it up again. Managing the electric energy consumption, and if we look at just the motors, we see that the major part, as said, 70% of the motors are in industrial applications somehow, like in pump systems. 75% of these motors are used for pumps, fans, and compressors with a substantial energy efficiency improvement potential. And why so? Because the electrical motor is a component that is usually have a long lifetime. We still meet motors up there that are more than 60 years old with quite poor energy efficiency performance. And how would you know what kind of performance you have unless they are monitored in a way that brings the understanding of what kind of actions are needed? So going back, the Paris Agreement, and we know that there are some regulated and visible losses out there, but what is the hidden potential and how to tackle those problems? Technology is already available. That is not the problem to improve the efficiency. Either we can, if we have fixed speed motors, and mentioned here, we can improve by upgrading the motors to a better energy efficiency class, or of course by putting in a variable speed drive where the energy saving can be even up to 70% based on how the motor is operated. And if we don't know how the motor is operated, then it's very difficult also to estimate what is the energy saving and the return of investment. Why do we then not know what is the motor operational performance? Well, typically motors below 100 kilowatts are usually never monitored in any way. So you know that you are wasting energy, but you don't know where to start. And I will present two different methods how this kind of things could start to be solved. Sorry, need to take some water. So the traditional method, what is usually done? So you go to site, you do some visual review of the installed applications. You and a partner of your, either ABB or somebody else, walk the site, and then you identify a pool of opportunities and target applications. However, due to time and resource restrictions, usually these opportunities are narrowed down to a few motors and pumps, because there is a limit how many you can handle actually by manual interventions. You need to go do some kind of data collection. In this case, you need to learn more a little bit about what kind of pump and motor, and that is usually found by looking at the rating plate data of the motor. That is very often a rating plate of the motor when it's operating in its nominal point. Then you need to understand the pump and the application, and then you need to collect everything using traditional methods and looking into also what are the site conditions. Well, then you analyze the data, you evaluate the potential for the savings, and you prioritize and you get a report and calculate what is the payback time and what is the risk and so on. And of course, there will be recommendations coming out of the calculations tool, for example, that ABB is using, and we will prepare you an action plan. Of course, a lot of elements are affecting the recommendations. It's not only purely based on the energy appraisal and the savings, also the age of the motor, what is the life cycle of the motor, is it a new motor, fairly new motor, old motor, do you need to replace it now anyway? Better to do it then now and get the savings instead of running to a failure, and then you have the double cost for replacing it, for example, like I presented there in a previous slide. This is the traditional method, and it's a very strong tool, especially when you look into big opportunities, bigger motors, bigger drivetrains, where you have a obvious saving potential already from the beginning. However, as I mentioned, usually due to time restrictions, you are not able to go into a huge factory and look at each and every motor manually, because it just takes too much time. So then leads to that you are focusing on usually variable torque loads like pumps and fans. Of course, over 90% of these are usually oversized and still running on partial loads. So you need to estimate then also how is it operated, and based on just a rating plate analysis, you will never know it, so you need to do some kind of manual measurements to calculate the power, and the question is then that how long time do you have to do this kind of analysis. And then you make the calculation and upgrade it, and usually when we talk about this, then we talk about also increasing the efficiency by putting in a variable speed drive on the motor. And of course, you can also find motors with poor efficiency that it doesn't need actually a variable speed drive if the motor is operating close to the nominal speed and power. But of course, you can do a upgrade of the motors, and you need to by entering into the new IE class, where you can also then have sustainable savings up to, in best cases, we have seen 10%, because a lot of the motors in the world are still even below the IE0 class, I would say. So this is partly as explained, the traditional method how you do it, and this makes fully sense to do every time you have the opportunity there. But there is also another way to do it if you are considering also to do better digitalized condition monitoring on your equipment. And digitalization, of course, brings one advantage to this by having data over a longer period. So the key areas to access the motor insights with digitalization is that you recognize the long-term trends. So by measuring and getting data, you see over a longer term, of course, the condition of the motor and the drive. You get a better understanding by the recommendations, maybe from the reports and the alerts and expert services, that what is the lifetime expectancy for the motor? Do we need to replace it already based on that, but could we combine it with the energy efficiency calculations? And leading to this, earlier, as I mentioned, it has been quite cumbersome and expensive to measure smaller motors in real operation and their performance. And the digitalization with a sensor or other methods bring us the insights, not only to do condition monitoring, but also power usage and operation. And this will then uncover the hidden energy consumers in the whole, say, for example, factory. So, and it enables then not only energy efficiency and sustainability, but also improved life cycle management, because you know the status of your asset, the condition of your asset, but also the performance of your asset when it comes to power and efficiency. Good. So this is pretty much the process then for energy efficiency analysis using digitalization. So pretty much it starts the same way as the traditional method, but you decide when you do this kind of factory visit or plan, you can then define which motors needs to be equipped with a sensor so that you can get the data. You have better freedom also then to go down in sizes, because you don't have the same restriction when it comes to time to be on site. Usually mounting a sensor takes something between 10 to 15 minutes per motor. You can then expand quite much more than doing manual energy measurements on the motor. Then the data is usually collected for, let's say, 3 months to 6 months to verify the performance and operation, finding out how the motor is operated, how many percentage of the nominal power is used. You get a better picture of also calculating reactive power, understanding that are we losing money by paying the energy company in the bill also for reactive power compensation? Do you analyze the data over the algorithms and the measurement period, and then based on that you do a action plan together with ABB, where you then can bring where you find the highest savings? Sometimes you don't find that big savings, but at least you have at least make sure for this yourself that there are no hidden losses in the in your facilities. And then you modernize your fleet and you continue to monitor the performance and savings and verify also the savings over a time period. Otherwise, with the traditional method, it's very often quite difficult to also verify your savings and what was the actual return of investment unless you have the assets connected and continuously getting new data. So in our opinion, to really make sure that you are getting the most out of it and you are able to do energy efficiency analysis on the whole, say in this case, a production facility and so on, I think that three more important things are needed. First of all, as I mentioned, it has to be plug and play. Otherwise, it will never make sense to do the analysis of tens, even hundreds of motors in the same facility if it is too cumbersome and costs too much. So it has to be very easy and economical. Secondly, the solution needs to be motor agnostic. With this I mean that the sensor and the data acquisition equipment you have and how you gather the data, how you analyze the data has to be made in the way that different motor manufacturers' motors can be investigated. It makes no sense to have a solution that is only looking into, for example, ABB motor or a Siemens motor or whomever manufacturer it may be. It has to be suitable for all motor manufacturers. And in the third place, you need to have domain expertise or domain knowledge of the electrical motor to really be able to analyze not only the energy efficiency as such, but also how to optimize. This goes then with how to choose the next motor. Does it make sense to put a frequency converter there? Usually it does, and so on and so forth. So this is what I refer to, that the value will increase when you have the information and when the information becomes actions. Sorry. So what will we then give to the customers when we use the data for energy efficiency insights? So the portal of the customer, the same portal that he's using the condition monitoring service of his assets, he will have a glimpse directly how his motors are performing. This kind of heat map with of his own fleet, of the loading, the efficiency, the reactive power, and so on, consolidated power usage over the whole fleet and the losses. And based on this, you can then do a estimation of the savings over time. So it provides a self-service for the customer about the motor efficiency. When the user then recognize that I have a significant or I have a high or whatever kind of opportunity here to save energy, and he see it from the fleet data, he can then order from ABB a detailed asset overview, where the report gives the very details of the motor operation, how the energy efficiency comes out, what kind of do we see other issues that can affect the return of investment, and especially also, as I mentioned, not only the active power but also the reactive power. That is usually a very hidden opportunity for the customer to save energy in his energy bill towards the energy company. So I have tried to avoid to go deep into the technology on the sensor itself, but I have just used one slide here, but how we are doing it in ABB. We are calling it the smart sensor. Today, our offering is a smart sensor generation 2. The sensor itself communicates wireless with a Bluetooth 5.0. It is certified also for hazardous areas, so we have no restrictions now where to use it. We have a sensor that has a long battery lifetime, up to 15 years. It's improved ingress protection here, so we have IP6667, meaning that it can be also a washdown on a washdown motor, for example, in the food and beverage industry. And we have now superior sensors inside the sensor itself, and I can just mention a few. We have acceleration measurements for the vibrations up to 20 kilohertz. We have onboarded a ultrasonic sensor up to 80 kilohertz. We have then also a magnetometer onboarded where we analyze the magnetic field of the motor, and that is of course used then for the power and efficiency calculations. And all these are then analyzed by our algorithms in the cloud and transforming the data into information and then also to recommended actions to the customer. Here I have just a few examples and detailed of our energy efficiency reports that we are providing to the customer. We have the fleet overview, for example, showing what is the energy consumption we are calculating based on, for example, the CO2 emissions can be estimated based on the country and average electricity production form, say a country with a huge coal fire power supply. Of course, the emissions and the savings in the emissions are higher, for example, compared to a country that has only hydropower and so on. And then we do showing quite in detail for each and every motor on request then how the performance, what are the savings, for example, if you change from a i80 to a IA3 motor. We are also showing the reactive power, we are showing the operational profile of the motor, so that, for example, the customer himself can even optimize his own process based on the utilization of the motors. So this was in a nutshell my presentation, and I'm open for questions. Sorry, I cannot hear you.
I have one question for you, Theo. Can you hear me?
Yes, I can hear you.
So I'm wondering, so when we use the ABB digital solution, where the data has been saved in the ABB cloud, that's right. So how long it will be, saved, or whether the user have to pay for the data access? Can they export the data from the ABB's platform? I'm wondering. So because a lot of maybe some third party and service companies or maybe consultants or experts like to take the data from ABB monitoring or condition monitoring, then
Yes.
for the analyze. So it's export. So how we can proceed such kind of process?
Yes. Yeah. So there is several ways to do it. If you are using, sorry.
Yeah.
So the data is available for download through REST APIs, cloud-to-cloud connection for the customer. So we are providing the customer the API keys so that he can download the data into whatever user interface he has of his own. So that is possible quite easily. It's not a difficult thing to do. Then he can also download the data in Excel format, or sorry, CSV format from the portal to his own and do analysis of the data.
Now I'm audible?
Yeah, another question about the sensor, because the one big problem of the sensor is the power supply. Actually, in industrial occasions, especially in factories, in a lot of high voltage occasions, the power supply for the sensor is a big problem. I know that ABB use the powerless, use battery, use called low power Bluetooth technology to transfer data from the sensor to the gateway. That's right. So
Right.
I know that technology several years ago, it can say 3 to 5 years. I think from your presentation, you mentioned that it can be used for 15 years. So how can you do
Yes.
that? So that's really, I think, big improvement last years. I think that's really interesting because I think that's a maybe new sense of the technology.
So it's of course how it's done. It's all about first of all dimensioning the batteries. It's about how you what kind of data you are sending up to the cloud. So pretty much what is consuming the battery the most is the data transfer to the cloud. And for that purpose, you need first of all to have a limited amount of data that you are sending up to the cloud. And secondly, you have to try to keep the data sending period as short as possible, because that is consuming the battery. So what we are doing, we are processing the data already on the sensor level and to a certain extent, and we are sending up what we call intermediate KPIs to the cloud, and there the algorithms are processing it into meaningful information and recommendations. And in case of that, you would like to have what we call raw data uploaded, then you can request raw data upload separately, but that is not happening automatically. So for example, the use case, we are sending data to the cloud, say every 1 hour. And at some point, like in my example, you started to see something happening on the motor, and you would like to understand that what is increasing my vibrations. Then you can do a raw data upload, where you then get in the portal already, for example, the FFT pre-calculated for you, and you can do on the time domain part analysis what is happening to your bearing, just as an example. And this is then for the expert to use. let's say the normal service engineer on the shop floor, he doesn't need this service. He just see that I have an alert, I need to look into it, and if he doesn't understand what is happening, then by transferring this, bringing up the raw data, doing the analyze automatically in our portal, he get the recommendation what to do. But it makes no sense to upload raw data each and every time because nobody is using it. And I'm going back again to my curve there, that data without any information and nobody using it is just waste of money.
And maybe also another question, because the motor, because of course sensor is costly. So maybe there is one minimum requirement or criteria how to select the motor system to be installed to the sensor. Because I think for the smaller motors, it's not worth to install such kind of stuff on it. Maybe like 20 or some 50 higher motors can be valuable to install such kind of sensor. Do you have any recommendations for such kind of size of choosing the sensor for the motor?
I would say that it starts to make sense usually around 10 kilowatt. But I have an example. I have seen a sensor mounted on a motor that actually the motor was almost smaller than the sensor itself physically. And of course, the sensor was more expensive than the motor.
Yeah.
But as the customer said, that it makes fully sense, because if this motor stops without warning, then I lose every time $100,000 in the process.
Yeah. Yeah. I mean,
so
the
there is
value
no
of the,
golden rule.
Yeah. Yeah. I mean, I understand in the value of the motor, I mean, the importance of the motor decides whether we install the sensor or not.
Right. Exactly. So
Okay,
there is a balance there. Yeah.
Yeah. No, I have no more questions. Maybe we can have questions from other audience.
I think we have. Thank you very much, Pego, for your wonderful presentation and your insight on this digital powertrain and the efficiency of motor aspect. So I think this is partly covered. What Musahid asked me is asking, what is the cost of digitization? His question is only this. Can you say something?
What is the cost?
Of digitization only, and he's not talking more like what type of and size this system, but only the cost of digitization.
The cost of digitalization, it's so difficult to say, and it's depending on where you are doing it. So, and how you are doing it. Digitalization as such is such a broad term that it can mean that you are gathering the data from manual measurements and putting it together in your own systems, or you are using data coming from wired solutions. Say that the sensor itself has a wire and it's wired to a PLC, and you have the wiring costs, and you have all other kind of infrastructure costs. Or you have wireless solutions like I presented here with the battery powered sensor. All cost is different. But where I can say that what I see happening in the world when it comes to digitalization, and there we see a very clear trend. Data is going to the cloud. We see less and less requirements for having data on the server on a factory level, because the maintenance, the updates and so on starts to be quite expensive in the future if you need to do and especially what is the value of the data if you don't have the latest version. So difficult question, cannot answer it directly. I can just put a example. Imagine if you would have a Google search engine on a server on your site. What would the value of that service be in, say, 1 year? You would never have the latest information. So all these things needs to be considered when you think about the cost.
Yeah, thank you, Kesu. I think this cost we covered in the yesterday Mr. Rolf session. He was saying that if we analyze the life cycle cost, then the energy cost cover around 97 or 98%, and this motor cost and other operation cost. Maybe digitalization may be considered in those costs, except the energy cost. So it may come, I think, within 5%, I think so. So most of the cost is covered by energy cost. If we go for the life cycle cost, Mr. Mahar, we have more questions. So thank you very much, Mr. Tesco, for your time with us and your excellent presentation. Mr. Ugo?
No more questions from my side, and I agree with Theo that the cost, it's very costly if you want to have huge data from either for the factory's own server or the cloud. Maybe a lot of people are maybe are concerned about the security or data security and also cyber security of the data being stored on the cloud server. But I think right now the cloud solution make some, if we don't control the data remotely, I think it's acceptable if you only want to store the data there.
Yeah. So I can comment on that. Cybersecurity, of course, a very important thing when you talk about data in general, not only in the cloud, but also on-premise solutions. You have to have the same cybersecurity measures also there. That's why you need to have also selected partners that know what they do, and especially on the cloud side, you need to have selected cloud providers that have this as the main focus. So that is one of the things. And the other thing that you need to think about, that what kind of data is critical that should never leave the site, and what kind of data is okay to be on the cloud. So what is the value of the data? I'm coming back to that statement again. If you have data that is monitoring the vibration of the motor every 1 hour, is it critical for your production? I don't think so. And that kind of data, for example, can very well be in the cloud. But if you have process data of how much production is coming out of your factory, that is another discussion then, of course. So that needs to be balanced also, because otherwise the cost will go throughout the roof if you really need to have same procedures for each and every data. So point is, what are you doing with the data? What would you like to get out of the data, and how important is it for you? This is also to balance. Thank you.
Okay, thank you, Mr. Tesco.
Okay, thank you.
Thank you.
Thank you very much. So, dear participants, we will wrap up today's session. Tomorrow we will start right at 2 o'clock in Pakistan time, and we will be covering by 3 resource person, Mr. Indra Bezmi from Switzerland, then from CNIC, and other Pauline Taylor from class USA. So thank you very much for your patience, and thank you very much for having with us. Thank you.
Bye bye. See you tomorrow.